Welcome to Academy. We are starting our series of videos on a subject that is exciting for many but puzzling for a few. I'm talking about the subject of calculus. In order to understand and appreciate the underlying beauty of the subject, you need to spend a lot of quality time in understanding the basics. If you have noticed, today I started off the video by writing all this gibberish on the whiteboard. You have function, 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 and function. Functions are fundamental to calculus as numbers are to algebra and angles are to trigonometry. Today in this video, we will try to get a very firm grip on the concept of functions. I must warn you that there are a lot of abstract concepts on your way, and I'm assuming that all of you have a very rudimentary understanding about the subject of sets. And I'm talking about functions in real numbers. Functions in complex numbers, we will do a separate set of videos later. We will start off with a very quick, short introduction about functions in a very unsophisticated street lingo. Here we go. Want to master calculus? Start with the basics. What are functions? In street lingo, functions are like machines or engines which take an input value, works on it, transforms it, and throws out an output value. The machine is also very dumb. It understands the input only if the input is in the machine's domain. If you input something that is not in the domain of the machine, it could actually blow up, as we shall see shortly. The collection of all possible outputs the machine can throw out is called its range. Here are a few examples. Exponential function. This machine takes an input and raises the input to the power of e, the Euler's number, which is a special irrational number, 2.71828 and so on. Squaring function, as the name suggests, the machine squares the input. Next is natural log function. The machine throws out the value of natural log, which is logarithm of a number, to base e, the Euler's number. Oopsie daisy, oh my god, the machine didn't like the input 0, so it blew up. Be careful while choosing your input. Don't feed anything that the machine doesn't like or understand or outside its domain. It is going to be messy. Next is a sine function. The output is the trigonometric sine value of the input. This function is a very nice one. It's very patient. It takes in all and any junk from negative infinity to positive infinity. But the output in real numbers is restricted to values within +1 and -1. You can represent functions as graphs in Cartesian coordinates in real numbers. We shall be using the graphical representations frequently in our discussions. Another tool that is very vital is the concept of intervals. It is often useful to evaluate a function across an interval of input values. There are two kinds of intervals, open interval and closed interval. In an open interval, the starting and end points are not included in evaluating the function. The mathematical notation for the open interval is a pair of curved brackets. On the other hand, in a closed interval, the starting and end points are included and written with a pair of square brackets. As an example, I'll describe the sine function in the interval 0 and pi. Based on our definition of open and closed intervals, we can make the following two statements. First one, the open interval statement. Sin x is greater than 0 and less than or equal to 1 in the open interval 0 and pi. So this is our open interval statement. Next is the closed interval statement. Sin x is greater than or equal to 0 and less than or equal to 1 in the closed interval 0 and pi. Notice that we have added equal to 0 to include the fact that sin 0 is equal to 0. With this quick sort of non-mathematical introduction to functions, we shall get a little more serious in life and discuss functions in a rigorous format next. Okay, after the non-technical introduction the concept of functions, things are going to get a little more formal. First, I want to read out the mathematically rigorous definition of a function. The definition goes like this. A function f from a set D to another set E is a correspondence that assigns the element x in set D to exactly one value y in set E. Sounds confusing? Let me break it down for you in this video. Let's say we have two sets, set D and set E, and the elements of set D are x, b, u and v, and let f be the correspondence, that is the function f. Let's call the correspondence as function f. Now the function f corresponds x to an element f of x in set E, b to f of b in set E, but it assigns u and v to f of u and f of v, but represented by a single element. That is, both u and v correspond to a single element in set E. Let me give you a very real world example. Let's say f is a squaring function. Let x be equals 3. That means x corresponds to f of x, 3 square, that is 9. Let's say b equals 6. B corresponds to an element f of b in set E, that means 6 square is 36. And let us say u is 4 and v is minus 4. Now f being a squaring function corresponds both plus 4 and minus 4 to a single element in set E, that is plus 4 square is 16, minus 4 square is also 16. So u and v correspond to a single element, that is the function f corresponds u and v to a single element 16 in set E. This situation is perfectly acceptable and is consistent with the definition of functions which I have written there. That is because it is corresponding an element in set D to a single element, that is exactly one element y in set E. So it is perfectly consistent and acceptable. Let's look at another situation. Let's say the function f corresponds an element in set D, that is x, to two different elements in set E. This is not acceptable. This is not acceptable as per the definition of the function, because it has to correspond exactly to one element in set E, whereas here in this case it is corresponding, that is the function is corresponding element x to two different elements in set E. Not acceptable. That is not a function. Now, in our earlier video I said functions are like engines, machines. They do a mathematical operation on the input and spits out an output. That's a very colloquial view of the function, because functions need not be mathematical operation. It need not be a squaring function. It need not be a logarithmic function. It need not be a sine function. It need not be a mathematical operation at all. Let's say the set D has, let's say, a book by Douglas Adams, that is The Hitchhiker's Guide to Galaxy. The function f counts the number of pages. So the function f corresponds the Hitchhiker's Guide to Galaxy in set D to 224. That is the number of pages in set E. Therefore, the function f is a logical operation. That is, it is counting the number of pages in a book. Or let's say the set D contains a red dot. The RGB value of the red dot is 25500. Okay? Don't worry about RGB values now. Just listen. The red dot has an RGB value of 25500. And the function f corresponds the red dot to a blue dot in set E with RGB value 00255. So the function here changes the color of the input from red to blue. Next, we shall see some more definitions. These are all jargons. You need to remember these jargons if you want a place in mathematics high table, unfortunately. But once you get used to them, you will be using them like a pro. Okay, next we will see two more definitions. The elements of set D are called the arguments of the function f, and the elements of set E are called the values of the function f. The arguments are called the independent variables, and the values are called the image of arguments under f. The next definition is the definition of domain and range of a function. The set D is called the domain of the function, and the subset R of the set E containing all possible values of x under the function f is called the range of the function. Not clear? We'll have graphs to our rescue. Let's see graphical representation of a few functions here, then we will be able to understand better. First, this is a quadratic function, that is x divided by 10 minus 2 the whole square, that is f of x equals x divided by 10 minus 2 the whole square. So this is a quadratic function, and this is the graph of this quadratic function. Examining the graph, it is very clear that every argument in the open interval minus infinity to plus infinity corresponds to a single value y. Therefore, the domain of the quadratic function is open interval minus infinity to plus infinity. And the range of this function is closed interval 0 to open interval plus infinity. But why left closed interval 0? Because at x equals 20, the value of the function is 0. That is, 20 is the root of this quadratic function. Therefore, 0 is included in the range. Therefore, the range of the function is left closed 0, that is, includes 0 to plus infinity. Next, we will look at the natural log function. This is the graph of natural log function, that is, f of x equals ln x. As you all know, natural log, for that matter any log, is not defined for 0 and negative real numbers. Therefore, the domain of the natural log function is open interval 0 to plus infinity, because 0 is not included, so it's an open interval. So 0 to plus infinity is the domain of the natural log function, and the range is open interval minus infinity to plus infinity. Next, we will look at the graph of the sine function. So this is a graph of a sine function. From the graph, it is very clear that the domain of sine function is negative infinity to plus infinity, but the range is restricted between the closed interval minus 1 to plus 1, because the sine function doesn't take any values outside minus 1 to plus 1. Therefore, the range of sine function is minus 1 to plus 1 within closed intervals. Next, we shall see what is known as the vertical line test to determine whether an expression is a function or not. What does the vertical line test say? If I draw a vertical line parallel to y-axis, it should cut the graph of the function at exactly one point. Then the graph represents a function, that is a proper function. Why so? If you remember, the definition of function says the function corresponds the element x in set D to exactly one element in set E. So that's the connection. That's why the vertical line test, the vertical line should cut the graph of a function at exactly one point. Now it is very easy to see that all the three graphs, that is the quadratic function f of x equals x square, the log function f of x equals ln x, and the sine function f of x is equal to sine x are all functions because the vertical line is intersecting the function at exactly one point across the domain of the function. So every function has to pass the vertical line test. It's a very intuitive and visual way to determine whether a graph represents a function or not. Remember, I had mentioned earlier that I'll give you examples of where one argument corresponds to multiple values. And we said those are not functions, right? We will give two more examples for that. Look at these expressions. Y square equals 4 minus x square and y square equals x plus 1. And these are the graph of these two functions. Look familiar? Yes, the first one is equation of a circle and the second one is a parabola lying in the side. Now, if I run a vertical line test, you can clearly see that the vertical line cuts these two graphs at more than one point. Hence, these two expressions fail the vertical line test for a function. That's why these two are not functions. They are just expressions. They are just equations. Now that we have had a basic understanding of what are functions, next we are moving on to limits. We are going to see how to define limits mathematically rigorous manner. I hope you enjoyed this video. Please like, subscribe to Academy and opt for notifications. As always, it has been a pleasure. Thanks for watching.